Okay. So, today we consider what we discussed, what we stated last time. We consider a very important topic which is called the characteristic functions. Given a random variable x with probability density p x, what is its characteristic function first? So, given x, random variable p x, probability density then the characteristic function of x is denoted as phi omega okay, this integral. It is something very similar to Fourier transform. Only thing is that in Fourier transform you have a minus sign here, here you do not have that. Okay. So, phi omega as such is a complex function of omega. Okay. Phi omega is a complex function of omega. It is called the characteristic functions or sometimes the first characteristic functions of the random variable x. Obviously, you can see that we can also write this integral as the expected value of e to the power j omega x, because we have seen given a function g x, its expected value is g x times p x integral. So, that is what is happening here. So, characteristic function is also characteristic function of a random variable x with probability density p x is actually the expected value of the function e to the power j omega x. Okay. Now, as you know, using the triangle inequality, we all know that but this is less than equal to, you know this triangle inequality, right? Sum of two sides is greater than equal to sum of third side, I mean third side. That we generalize, and in the case of here it is not discrete sum, but it is a continuous sum. So, mod of a summation, mod is equivalent to the length of the overall summation, okay, is less than equal to the individual lengths. Okay. So, if you apply that, so summation individual magnitudes p x and magnitude of this is 1. So, it turns out to be this, and mod of p x and p x they are same, because p x is a real and non-negative valued quantity. So, this is actually minus infinity to infinity equal to 1. So, you see this characteristic function magnitude is upper bounded by 1, okay. And when is it equal to 1? You can see that what is phi 0? Phi 0 is nothing but p x dx, because e to the power j omega x at x equal to 0, at omega equal to 0 is 1. Okay. So, you have p x dx which is 1, which means phi 0 is real and its value is 1, and the function phi omega, the magnitude of the function phi omega, okay, attains its maximum value of 1 at origin at omega equal to 0, and the magnitude falls after that. Okay. So, this is the property of the characteristic function. I repeat, phi omega, its magnitude rather, it attains its maximum value at omega equal to 0, that is at origin, and the maximum value is 1. Maximum value is 1, and then at all other omega other than 1, other than 0, its value, its magnitude is less. Okay. Now, you can generalize this concept. Okay. You can generalize this concept and get some other definitions also, which are also equally useful. One of them is called the moment function, rather moment generating function. Here instead of phi I put a underscore. So, phi underscore and it is not omega, it is a general complex variable S, something like what you are familiar with in the case of Laplace transform, where S is a general complex variable. This is this. Which means we can also write it as expected value of this function e to the power s x. And as before you can see phi underscore 0, if you put 0 here, this is 1 and integral of p x dx, that is 1. So, phi underscore 0 is 1. Okay. And then there is another function that is called second characteristic function. Here instead of taking the phi omega or phi underscore omega or phi underscore s, we rather concentrate on their logarithms. Okay. So, instead of phi omega we take ln of phi omega, or instead of phi underscore s we take ln of phi underscore s. Both are second characteristic functions. Okay. So, the second characteristic function psi omega is nothing but ln phi omega. Okay. And you can see what is psi 0, ln phi 0, but phi 0 equal to 1 we have seen. So, this is equal to 0. So, when you are dealing with phi omega, you take ln of that, you get psi omega, and psi omega is your second characteristic function. But suppose you are dealing with the moment function or moment generating function phi underscore s. I am putting underscore because phi and phi underscore, they are two different functions, and also it is a function of the variable omega, it is a function of the general complex variable s. If you take ln of that, instead of doing here, instead of doing this, if you take ln of phi underscore s, then again you get a different function, I call it psi underscore s. This is also equally useful. Okay, either you live with this definition psi omega or psi underscore s, and as before psi underscore 0 ln phi underscore 0, and phi underscore 0 was 1 we have seen. So, this is equal to 0 as before. Okay. Now, you see one thing, suppose x is the random variable and you know its probability density function p x, and y is a function of x given, linear function of x given by this equation y equal to x plus b. Then what is, and y has its own probability density function p y y, where this is just a symbol, where this is the variable. The y within parenthesis is the variable actually, and this subscript y is just a symbol showing that, meaning that this is a probability density of the variable y, and x is a random variable that has got probability density p x x. Once again this x within parenthesis is the actual variable, and this subscript is x denotes that is a function for the random variable x. Okay. Then what is phi y omega? This is nothing but expected value of right, but y is a x plus b. So, this is again and you have this quantity, this outside expected value of A x, which means e to the power j omega b phi x, not omega, but a omega. Okay. This is a very useful relation and used in practice. As an example, see this. Suppose x 0 mean Gaussian with variance in that case, what happens to phi x, that is expected value of e to the power j omega x. This is nothing but e to the power j omega x multiplied by the probability density e to the power e to the power minus x square by twice sigma square dx, because it is Gaussian. This integral is well known, I am not deriving it. I mean, this is a standard result for this integral, that is equal to e to the power minus sigma square omega square by 2. Okay. This is for the 0 mean random variable. But now suppose now x is not 0 mean, but it has got a finite mean mu. Okay, then what happens? That is, first let me erase this. Suppose y as a is a 0 mean is a random variable once again Gaussian with the same variance sigma square, but a mean mu, which means y is actually x plus mu. Okay. What will be the characteristic function now? What is phi y omega? Phi y omega, as we have seen, is nothing but this equation you can interpret as a x plus b. So, a equal to 1 and b is mu. So, from our previous result, it will be to the power j mu omega and then phi x a omega, but a equal to 1. So, you will get this thing, this quantity only. Okay, which means by 2. Okay. So, given a probability, given a random variable x with probability density p x, okay, we can compute its characteristic function by taking the integral. But given a characteristic function, how to get back the corresponding probability density? So, it is we can obtain that by just applying the well known results from Fourier transform, where on one hand you have got the direct Fourier transform, which gives you the function in the Fourier frequency domain, and from frequency domain you can calculate the, you can get back the time domain function by the inverse transform, right. So, the same thing can be applied here. You can see one thing, I repeat, we had phi omega is equal to this was plus Okay. So, this is nothing but Fourier transform of P x at minus omega. Okay. Or in other words, if I put a minus here, you get a minus here. Okay. So, phi minus omega then I put plus. If you put phi minus omega, then it becomes simply Fourier transform of P x at plus omega. Okay. So, that means what is P x? Inverse Fourier transform of phi minus omega. So, P x is IFT, inverse Fourier transform of phi minus omega, which is nothing but 1 by 2 pi phi minus omega e to the power j omega x d omega. Now, you replace omega by minus omega. So, d omega becomes minus d omega, okay. A minus sign comes. Here you have got minus sign e to the power minus d omega x, this becomes phi omega, outside have a minus, but the limits becomes plus infinity to minus infinity. So, if you want to again make it from minus infinity to infinity, a minus will again come. So, the two minuses cancel each other. So, what you get back is the following. That is replace I repeat d omega becomes minus d omega. So, minus sign would come here, but limits becomes from plus infinity to minus infinity. So, if you reverse it again a minus sign comes. Okay. So, if you want to stick to minus infinity to infinity, another minus sign will come. So, they will cancel each other. So, you get back what you had, and minus omega replaced by omega means it becomes phi omega, and this becomes you get a minus sign here. So, this is the inversion formula from the characteristic function how to get back P x. Okay. Next, we consider that moment function phi underscore s. What was it? This was P x e to the power s x dx from minus infinity to infinity. If I differentiate both sides with respect to s, I repeat with respect to s, that is s n times, what happens? If you differentiate once, x will come here. If you differentiate again, another x will come, and likewise. Okay, e to the power s x, if derived with respect to s, you get back x into e to the power s x, then x square e to the power s x, x cube e to the power s x, and likewise. So, n means nth order derivative, it is not power. If I say phi n s, it means nth order derivative of phi s with respect to s is nothing but then what happens? If s equal to 0, s equal to 0 means this becomes 1, you have got this quantity which is nothing but expected value of x to the power n, which is nothing but nth order moment. That is why this function is called the moment generating function. We can use it, that is first you differentiate with respect to s maybe n times, then put equal to 0, n equal to, put s is equal to 0, what you then get is nothing but the nth order moment. Okay. So, once again see this formula, you differentiate the function phi underscore s, let me put it underscore, I forgot to put phi underscore s n times and then put s equal to 0, that will give you the nth order moment. As for example, if n equal to 1, then what happens? Okay, if n equal to 1, then what happens? In the integral you have got x to the power n, which is nothing but x, at p x dx, in fact that is equal to E x, that is mu, and what is 0? That is now n equal to 2, phi double prime means second order derivative at origin at s equal to 0. What happens to that? That is nothing but, as we have proved earlier, x square p x dx and we know this is equal to mu square plus sigma square. Okay. Mu was first order moment m1, this is second order moment m2. Okay. So, you can see this. One more interesting thing we can now consider. We all know Maclaurin series. You can expand phi underscore s as phi underscore 0, then s into s prime, then x square by factorial 2 dot 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 s to the power n by factorial n this n means actually nth order derivative plus dot 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 dot. Okay. Of course, this Maclaurin series converges near s equal to 0 if all of them phi 0, phi prime 0. In fact, you can write them as, we know, we have seen earlier that phi underscore 0, okay, this is equal to, this is equal to 1, right, this you have seen. Okay. Anyway, phi nth order derivative, phi nth order derivative of this function phi underscore s at s equal to 0, that is nothing but, this quantity is nothing but m n, nth order moment. So, this summation actually you can write as s to the power n from 0 to infinity. Okay. This of course converges to phi underscore s near is equal to 0 if converges absolutely if these moments, okay, are finite. Okay. If the moments are finite, then the series converges absolutely near is equal to 0. Okay. But that is just a mathematical point. Now, see one thing, from phi underscore s we can get back our original probability density function for the random variable x, which means any probability density function can be equivalently and exactly described by all its moments. Okay. Earlier we have seen that given the probability density function, we can find out this moment generating function and from that all the moments. Now, this is a reverse phenomenon. Given all the moments, by this series you can find out phi bar s, and from phi bar s you can find out phi underscore s, and phi underscore s, from that you can find out what is the original probability density function. Okay. Let us now take an example. Suppose, so this is an example. Suppose x has exponential density. Sorry. P x is actually lambda, lambda is a parameter, e to the power minus lambda x u x. U x actually means it is a unit step function, that is for x equal to x less than equal to 0 minus for all negative x this is 0, okay, and for all x greater than equal to 0 this is 1. So, this probability density has got value 0 for all negative x, and for all probability for all x greater than equal to 0, that is for all non-negative x, its value is lambda into to the power minus lambda x. Lambda is a parameter which is found out by integrating this with respect to x and equating that to 1, lambda is found out. Okay. Now, for such a function, what is phi underscore s? Very simply, we take the integral and take it from 0 to infinity only, because this function, this unit step function is present, okay, and lambda which goes outside e to the power minus lambda x. So, p x times e to the power s x. If you integrate, this becomes, you take e to the power minus within bracket lambda minus s, then x. If you integrate, then at x equal to infinity that will give rise to 0, at x equal to 0 you will have 1. So, there will be a factor lambda minus s below. So, you have this. Okay. So, what is that is equal to, if you differentiate, you have got lambda minus s to the power minus 1 here. So, that becomes minus 2, a minus comes, that gets cancelled because another minus comes from here. So, meaning is 1 by lambda, which is equal to first order moment also equal to the mean. Okay. And what is this? Another derivative, again it becomes 3, a minus sign comes, but that gets cancelled to the minus sign coming from here. So, it is lambda by lambda minus s. Okay. Similarly, this is equal to lambda by whole square this should be 3 and here should be 2. Okay. The minus signs get cancelled with each other. So, what happens to this function? This is equal to 0 is simply 2 by lambda square. This is m2 as we have seen, which is nothing but mu square plus sigma square, meaning mu is already we have already seen mu is equal to 1 by lambda, so 1 by lambda square, which means sigma square is 1 by lambda square. Okay. Next, we consider another very important function, which is called cumulant. Now, earlier we have been, so long we have been considering the characteristic function, or last time we considered the moment function, that is moment generating function. But as we have done, as we have stated in the very beginning, there is another class of function that is called the second characteristic function, where we do not take the characteristic function as such or the moment function as such, but take their logarithms, right. So, we will be using that. So, again we recall we had psi bar s is nothing but ln phi bar s, and also we recall that psi bar 0 was ln phi bar 0, but phi bar 0 is what? That we have seen is equal to 1. So, this quantity is 0. Okay. Then we define the nth order cumulant lambda n actually you differentiate this psi bar s with respect to s n times, then substitute, then put s equal to 0. Okay. The first question is, what is lambda 0? Lambda 0 means no derivative, but that means we have only psi bar 0, but what is psi bar 0? That is 0. So, lambda 0 is 0. Then we go for, as before, we go for the Maclaurin series expansion. This is psi bar 0 plus s times Okay. At this quantity psi bar 0 is 0, this quantity psi prime psi bar 0 prime, that is single derivative, that was lambda 1, then we have got lambda 2 and so on and so forth. So, nth order derivative of psi s, psi bar s, and then at s equal to 0, that is lambda n. So, this you can write it as lambda 1 s plus lambda 2 s square by factorial 2 dot 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 lambda n s to the power n by factorial n plus dot 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 dot. Okay. One more thing, we say that lambda 1 will be same as mu and lambda 2 will be sigma square. How? I just give you a minute to think. I repeat, lambda 1 equal to mu and lambda 2 sigma square. Just think for a minute. I do not think it is very difficult. Anyway, let me work it out. We have seen that phi bar s, right, ln of that was equal to is equal to psi bar s, which means this is nothing but e to the power psi bar s, right. So, if you differentiate it with respect to s once, what you get? You get this thing first and multiplied by the derivative of this. So, psi bar s, derivative of psi bar s multiplied by this, okay. Meaning what is this? But as we have seen, psi bar 0 is 0, e to the power 0 is 1. So, this is equal to this. But what is this quantity? This quantity is m 1, this is equal to m 1 equal to mu, okay, and this is equal to lambda 1. So, this is proved. Okay. So, we come to the next thing. What happens to, well, we have just now seen that phi prime bar s is this. What happens to the second order derivative? Differentiate this, hold this, and then hold this, differentiate this. Okay. So, if you differentiate this, it becomes psi double prime s, this quantity goes outside, and if you hold this and differentiate this, you get back psi prime s again. So, it is square, which means lambda 2, which is nothing but this is equal to plus, sorry, this is actually M2. Whole square, and e to the power, as you have seen, e to the power psi 0, that is equal to 1, because psi bar 0, psi underscore 0 is 0. So, this is equal to 1, so I do not write it. So, you have got this quantity, which is nothing but, this is nothing but lambda 2, and this is the lambda 1 square, but lambda 1 is same as mu 1, we have seen. So, this is mu 1 square, and we also know that M2 is nothing but mu square plus sigma square. So, if you compare, obviously lambda 2 equal to sigma square. So, this is proved. Okay. Cumulants I will not consider any further, but you should always, I mean, remember this function, because this has got tremendous use. Okay. Finally, given x and p x and a random variable y which is a function of x, we know we have seen already that given the probability density of x, say p x x, how to get back the probability, how to get the probability density of y, p y y, how to get this. But while doing this, you can also make use of the characteristic functions. Okay. What is phi y omega? Sorry. Okay. But y is g x. So, this is nothing but expected value of e to the power j omega y, but we know y is g x. So, you can also write it this way, e to the power j omega g x p x x. Now, suppose you start with this integral and you can write it by some manipulation. Suppose you can write it in this way. You can write it like this. Suppose this integral you can write by some manipulation like this. E to the power j omega y, which is the first quantity, it is by j omega g x, or it is by j omega g y, just same, times some h y dy. Then just comparing this with this, you can see that h y should be equal to p y y. Okay. So, we first write this equation, then try to write it in this form. Whatever h y comes out, that will be equal to p y y. We just consider an example and then we call off. X, the symbol means actually n for normal, which is same as Gaussian. This means Gaussian random variable mean 0, variance sigma square. Okay. all right, and given that y is equal to a x square. Okay. Now, we know what is phi y omega. We can write it simply like e to the power j omega y, which is a x square, and p x x we know 1 by root 2 pi sigma e to the power minus j, sorry, dx. Since we have only x square here, we can take the integral from 0 to infinity and multiply it by 2. So, in that case this integral becomes times 2 okay. All right. Now, in this interval 0 to infinity, we have got of course the function y equal to a x square, but within the interval 0 to infinity, the relation between y and x is 1 to 1. For any x you get only one y, and for any y you get only one x. Okay, and there you have got dy, which is twice a x, dx, which is twice a, y equal to x square. So, x equal to square root of y by a, okay, dx, which means twice this. So, dx is nothing but dy by twice square root square root a y, and the first quantity is e to the power j omega y. Okay. So, you can always write it like this. There is a 2, but that will cancel with this 2. Then e to the power x square, as you know, is minus y by a, y by a, and then you have got this function 1 by this. Okay. Which means this quantity 1 by root 2 pi sigma e to the power minus y by twice a sigma square into 1 by square root of a y. This is your p y y. sigma square root 2 pi a y. Okay. And of course, this is on the positive side u y. Okay. U y obviously, whether x takes negative or positive, y can always take only positive values. So, for any negative y, negative value of y, the corresponding probability is 0 because it just cannot take place. So, I stop here today, and we start with the next new topic next time. But if there is any question, I would suggest that you all consider all these theories and try to solve some problems on your own from Papoulis. Also, please go through the worked out examples, because due to time constraint I can't take up these worked out examples which are already there for you to read. Okay. So, that is all for today. Thank you very much. Okay. So long we have discussed just one random variable and function of one random variable. Okay. We so far did not discuss what is called joint variation. That is, earlier we considered a random variable x, its probability density, probability distribution, and a function of this random variable and all that. Similarly, there could be a separate random variable y. We discussed its properties and all that. But there is an important topic actually where x and y, they are two random variables which are mutually related. That is, the underlying process is such that x and y has got some kind of interconnection, interdependence rather. Okay. Then the question of not individual variation, but rather joint variation and joint statistics comes. For instance, you can consider these two variables. One is say temperature of the environment, okay, and humidity in the environment. Now, temperature could be a variable T, humidity could be H. Now, you all can visualize that the underlying physical process is such that definitely one depends on the other. Surely, if the temperature is high, there will be some kind of one type of humidity. If the temperature is less, another type of humidity, and vice versa. Okay. Now, we do not go into this physical modeling because that is very difficult, but we treat both T and H as two separate random variables which are jointly related, mutually related. Okay. Obviously, because if T is high, maybe H will be less or H will be high. Again, if H is less, T could be high, less, because that is determined by their mutual interdependence. Okay. So, we define. So, our topic today is in fact, now we are considering two random variables, but in general it will be say n number of random variables. Okay. So, we will extend this concept to more than two number of random variables. So, we now consider always a pair under this topic, always a pair. X is a random variable, y is a random variable, but since they are related, we consider x, y. Okay. In that case, we have to define the joint probability distribution of x and y. Now, what does it mean? Let us give a definition actually. We consider the event. This random variable x taking value less than equal to some given number capital X, y taking value less than equal to some given number capital Y, okay, which actually means this pair is taking value from a particular region D in the xy plane. What is that region? Suppose this is the xy plane
x y, and this point is your capital X capital Y, then if you draw this line, this area is D. Okay. Obviously, within this area, both these things for discrete variables also. Suppose x and y, they are two discrete variables. X takes values from this set. I mean, why? I mean, it may not be finite. So let me not put it this way. Xi, Xj, and like that. It could be a finite set, it could be infinite set. Similarly, Yk, Yl, dot dot, like that. Okay. In that case, the joint probability that x takes the value xi, y takes the value yj is denoted by Pij. Obviously, I and j can put a double summation, that should be equal to 1, excuse me. Okay. And Pi, that is obviously Pi k, and summed over all possible k's, that will be Pi. Okay. If Q j is the corresponding probability of y equal to y j, this will be again equal to Pi is the probability of x equal to xi, that is this summation. Pik is the joint probability, and here it is Qj is nothing but again Pi j, but summed over I. Okay. This is pretty obvious. So, in today's class we conclude here, we will stop here. Okay. We continue to expand on this theme, getting into what is called probability mass, then a very important concept called statistical independence, then joint characteristic functions and things like that. That will be for the next time. Okay. Thank you very much.